All right. So in this whole section, we've been talking a lot about crystallography and directions and points and planes and the densities related to those. And I get to the point where I want to talk about now sort of the practical limitations of crystallography. And that's where I get to this idea of real crystals. So when we talk about a unit cell and we talk about a crystal structure, we think of those as these infinitely repeating three-dimensional structures. So this is all hypothetical, though. In a real life, a real crystal, an actual crystal, is going to have to end at some point, right? And so instead of it going off into infinitum, we're going to have it terminate at some point. And so now we look at where it terminates, right? And so this crystal, with its structure, is going to terminate, and it's going to do so at specific planes, right? So if we look at a gemstone, a naturally occurring single crystal, you see here that this is a gemstone, and you see the facets, right? What we call facets when we study minerals. Well, these facets are the same thing as particular planes in that unit cell or in that structure, right? So basically that crystal has truncated or terminated on a specific plane within the structure. And so that's why we get these facets at very particular angles, because there's specific angles between various crystallographic planes. And so this is how this is one way a crystal can end. If we have this giant single crystal, we have something like a gemstone, right? A single crystal. But also another way that materials can end is actually to have, and this is just a two-dimensional representation, but if you think of each one of these as a crystal, right? It ends at certain points, and so you'd have something that looks like this if you look at 3 dimensions. However, this is also bordered by another crystal, and then another, and then another. And all of these crystals, you can see, are at different angles to one another. And they're all contained in one material. So we have these multiple crystals where the end of one crystal starts the beginning of another crystal. And the area between these, the boundary, so to speak, between these grains are known as grain boundaries. So each one of these is a single crystal, but it's inside of a greater material. And so this is what we tend to call a polycrystalline material, because we have multiple crystals, so poly, in one material. So things like gemstones, you're familiar with those. Those are single crystals for the most part. But most materials that we deal with on a day-to-day basis tend to be polycrystalline in nature. And so we'll talk about the various aspects between these two types. So along with that, if we think about a single crystal like that gemstone, what we see and why we care so much about understanding directions and planes is because that properties can vary with direction. And this is known as anisotropic or isotropy, when a property depends on directions. So for an example, we talked very briefly about this modulus of elasticity. So basically stretching something, stretching the bonds, and how much force it takes. That's the very brief explanation of that. Well, if we think about it, if we look at this body-centered cubic structure here, this is actually iron. If we stretch it along this direction, the atoms are packed in one way, whereas if you stretch it along the edge, the packing is different. And so we'd expect, because the bond distance is different, that the curve and the modulus would be different as well. And that's what we see. We see that the modulus along the edge, which is the 100 direction, is 125 gigapascals. However, in this more close packed, or this close packed direction, which is the 111 direction, which is diagonally through the cube, the modulus is much higher, 273. So it takes a lot more force to stretch it along this direction compared to this direction. So that's the anisotropy that we're talking about. Properties changing with direction. And this can be seen with single crystal materials, because there's different packing and therefore bonding is different in these different directions. So like I said, we have single crystals, but we also have polycrystalline materials. So those are those materials that have a bunch of smaller crystals and they're joined together at these boundaries. So we think of these materials not as anisotropic, where the properties depend on direction. Instead, these are isotropic, so they don't depend, or they're independent of directions. And let me see if I can kind of explain this to you. So polycrystals, so this is an example. This is a micrograph, an image of the microstructure. So each one of these light areas surrounded by the dark areas, each one of these is a grain. And each grain, like we saw in the sketch here, is at a different orientation. So we know that within one of these grains, which is a single crystal, it's going to have those properties like we saw here. So if this is iron, right, we know this direction and this direction, the elastic modulus is quite different. So if we just test one of these crystals, that's the case. However, all of these grains that you see, and this is just a small snapshot of the material, but all of these grains are at different angles. So this angle here may be this angle over here in this crystal. And so what happens there is that all of these different directions that the elastic modulus in this example may vary become averaged out, because we have so many different crystals with different orientations. And so the fact that we have all of these polycrystals randomizes that elastic modulus. And so for a polycrystalline specimen of iron, the elastic modulus is 210 gigapascals, which is, if you look at the previous slide, somewhere in the middle between these two, right? Because all of these have been kind of averaged together because we have so many different grains. So most polycrystalline materials we think of as isotropic. So the properties are independent of direction. So if we test this material, whether we test it in this direction or this direction, we would expect the elastic modulus to be 210. There is one caveat to this idea, and that is, if we think about that same iron material, if you're familiar with the process of rolling metal, we basically put it through rollers, and that is to form it into thinner and thinner sheets. Well, when we do that, what happens to this polycrystalline structure is it gets elongated along that direction that we rolled it and squished it. So in this case, the act of rolling it does what we call texturing, in that it now can have a preferential direction. And so in this case, things tend to get aligned along this direction. And so this is one of those cases where we can actually have some anisotropy because there's a certain directionality to these crystals elongated along this rolling direction. But for the most part, we think of most materials that are polycrystalline as isotropic. All right, so we've done all of this discussion in these past sections on structure and crystallography, talking about crystal structure and crystallographic features, but everything we've done relies on these sketches, right? These sketches of the simple cubic, the BCC, the FCC, hexagonal close packed, right? Well, you may be wondering, how did we determine these crystal structures? If you think about it, they're really small, right? They're the size of atoms. They're on that order of magnitude. So how do we determine crystal structures? You know, optical microscopy can only go to such a high magnification. So we can't use optical microscopy to do this. We need something that will probe a material at that length scale of atoms such that we could determine its crystal structure. And so this is where the next module is going to come in, and it's going to tell us how we determine crystal structures and what technique does that.